Alright, so what we've got is we've got a bullet. I have two scenarios. In the first scenario, it says the bullet and the block slide off the table and hit so it gets stuck and they go off together. In the second scenario, the bullet actually passes through the block, so the bullet goes like this, and then the block will start moving and, of course, follow after. They're just not physically stuck together. I want to know in which case is the block going to land the farthest away. So how I thought about this is the one that lands farthest away is the block that is moving the fastest. The block that is moving the fastest has the most momentum. We know that the block at first was at rest. The block's momentum has to come from somewhere. It's going to come from the bullet. We know that total momentum is conserved, so we know that the bullet is going to lose momentum and the block is going to gain momentum. We know that the amount that the bullet loses is the amount that the block gains because conservation of momentum. So whichever bullet loses the most momentum is the block that gains the most momentum. So if we're looking, we've got two options. The bullet can pass through or the bullet can get stuck and move with the block. In the case, I think it's scenario 1, where it gets stuck, this bullet slows the most. This bullet barely slows down at all. It is going to slow down because it's going to pass through and give a little bit of its momentum, but if it's passing through, it's not slowing down very much. The one that slows down the most has the greatest change in velocity. Greater change of velocity means greater change of momentum. If this bullet is losing more momentum, that means this block gains more momentum. So if we're talking about scenario 1 and scenario 2, in scenario 2, the bullet doesn't lose very much momentum, so the block doesn't gain very much momentum. Here, the bullet loses a lot, which means the block gains a lot. So I'm going to start, we worked backwards, right? The farther comes from the faster comes from the block that has the most momentum, the momentum comes from the bullet. How much the bullet lost more in this one, so that's why it's greater. So now my explanation is going to be the forward. So in scenario 1, the bullet slows more than scenario 2. So it has a greater change in velocity in 1. A greater change of velocity, so I'm going to say so has a greater change in momentum. Because total momentum is conserved, the change in momentum of the bullet is the change in momentum of the block. So what we're saying is that the bullet has a greater change in velocity in 1. That means the bullet has a greater change in momentum in 1. Total momentum is conserved, so the change of the bullet is the change of the block in each case. So the block in scenario 1 has a greater momentum, change in momentum. So it is moving faster, so lands further away. Alright, so that's what I just came up with off the top of my head. Here's what I'll say it might be slightly different, so I'll put what I wrote when I was thinking slowly. In scenario 1, the bullet slows more than the bullet that passes through in scenario 2, so the bullet has a greater change in velocity and therefore a greater change in momentum. I'm going to say in 1 because it wasn't super clear which one I was talking about. Since total P is conserved, the bullet's change of change of momentum is the block's change of momentum. The block in scenario 1 has a greater gain in momentum, so it's moving faster. That means it moves a farther distance, x, because they have the same time, but a greater speed will go farther. So basically the same thing. Number 2, we've got two situations where the block comes in with a velocity v and sticks to a block of 3.5 m. In which case will they be moving faster after? So some people actually did the math, and you can do the math, and that'll help you at least decide your answer, but that's not really an explanation, because I'm saying which one and justify, so I want you to explain. You should be able to look at these two. Either way, you're picking up 3.5 m. So either way, I know that like when they stick together, this velocity is going to be slower than B. But they're not going to slow down by the same amount, even though they're picking up the same mass, because this one is coming in with more momentum. So because I'm coming in with 2m, and that 2mv is shared over 5.5m, instead of mv being shared over 4.5m, I'm starting with more momentum, so that means I have more momentum in the system, so it's going to go faster. So I'm going to call this like A and B, because it wasn't labeled for me. So B starts with more momentum in the system because has more mass with the same velocity. And the reason I'm saying that is like I could very easily have more mass but not have more momentum. Think if I had M and 4V and 2M and V. This one definitely has more mass, but this one definitely has more momentum. So it has more momentum because it has more mass with the same velocity. So will the blocks have more total momentum after in B, which means that they'll be moving faster. Here, block of mass M moves with the velocity v naught. This guy is initially at rest, and then they collide and stick together and swing up to some height, and I want to find what this height is. So first this is collision, which means conservation of momentum. So mv naught plus 0 goes to mx plus mx, because both of them are not stuck together. So 2mx equals mv naught, divide 2m over, that's just 1/2 v naught, or v naught over 2. Now I have the m and the m moving at 1/2 v naught, and they're going to swing up to m and m at a height of h. That's conservation of energy, because I'm swinging, I'm changing from kinetic energy into potential. The kinetic at the bottom will equal the potential at the top, so I've got 1/2 mass of 2m, velocity of 1/2 v naught squared, equals potential, still mass of 2m, g, and a height h. First thing I'm going to do is I'm going to get rid of the 2m, so get rid of the 2m like this. I'm going to clean this up, so that's 1/2 squared is 1/4, v naught squared is just v naught squared, equals gh. 1/2 times 1/4 is 1/8. And then to get h by itself, you just divide g over. So v naught squared over 8g, or 1/8 v naught squared over g, same thing. Some of you left it as 1/2 v naught squared over g. That's also correct, just not very neat. Alright, we've got two small balls, identical density and size, that means they're the same mass, fired from a toy gun towards a wooden block. Ball A is elastic and is going to bounce back. It just means it's like a bouncy ball. That's what it means. It's going to bounce backwards after striking. Ball B is made of clay and sticks to the wooden block upon impact, which is moving faster. So this is the before case. In A, you've got the ball bouncing back, and this one is going to go forward. And in B, you've got the ball and the block going together. I want to know in which case is the block moving faster. So there's two ways to think about it. One way is you know that your total momentum, so total momentum is going to be to the right, because before you had momentum to the right and 0, so total momentum is to the right. If this turns around and goes this way, that means that this is going to have to go pretty fast in the opposite direction to not only continue with like this guy's momentum, but to make up for the negative momentum. So this negative plus this positive still has to add to positive. So I have more momentum this way. Whereas here, right, this one, I still have momentum to the right, it's just a little bit less, so that means this one only needs a little bit to add up to the same total as before. That's one way to think about it. I find it easier to think about change in momentum, so very similar to what we did for number 1. If you look, the block that gains the most momentum, we know that that's the one that's going fastest, and that one gets momentum from the ball's change in momentum. So whichever block has more momentum after is just whichever clay ball or whatever ball changed the most momentum. The ball that changed the most momentum is the one that went in, turned around, went back the other way, compared to the one that just slowed down and continued in the same direction. So I'm going to say ball A has a greater change in velocity because the velocity changed directions. So ball A has a greater change of momentum because change of momentum is m delta v. If both balls have the same mass, right, more change of velocity means more change of momentum. All right, now what the ball's change of momentum has to do with it is, since total momentum is conserved, the change in momentum for the ball is the change in momentum for the block. Obviously not the same sign. One is gaining, one is losing, or one is positive, one is negative. So since total momentum is conserved, change of momentum for the ball is the change of momentum for the block. The change of momentum is greater for the block A. So I'll just say, because block A has more momentum, that means it is moving faster because they have the same mass of the block. So if one has more momentum, it has to have more velocity. All right, cart of mass m is released from rest, and there's another cart m waiting for it. So first I want to find what is the velocity of this cart when it gets to the bottom. And then I want to know, okay, m is coming out with some velocity, it hits m, and then the two are going off, and this is my end goal, to find this velocity that they are going off together with. But first I'm going to find the velocity it comes down with. That is potential going to kinetic. mgh is 1/2 mv squared. 2gh is v squared, so the velocity is square root of 2gh. Not my answer. That is the velocity it comes down with. So I'm coming down with 2gh right here, and then I'm going to hit some mass. This is collision, so we're going to use conservation of momentum. So momentum before is m coming in with the 2gh velocity plus the other guy's 0 equals mx plus mx. So I'm looking for the velocity. You could say 2mx, which is what I'm going to jump to. M squared of gh, divide 2m over, and then m and m cancel out, so you've got square root of 2gh over 2 is your velocity that they go off together. Which should make sense because I'm coming in with this velocity and I'm picking up an identical mass, so it should exactly half. So whatever I came down with, halved. Alright, now if my original cart that was released was actually at 2m at the top, what would the velocity at the bottom be? So the velocity at the bottom we found was square root of 2gh. What mattered was the height it was dropped from. The mass actually didn't matter, so it's going to be the same. When we do it, so I would actually just write velocity is square root of 2gh. Doubling mass has no effect on the velocity at the bottom. You can also say it has, so like why people think it's going to come down faster is they're saying, oh, I start with more potential energy, and that's absolutely true. You have 2mgh instead of mgh, but then at the bottom, you do have more kinetic energy. That more kinetic energy comes from having more mass, not because it has more velocity. So I actually come down with the exact same velocity. The velocity of the collision, of the cart's post-collision. So think about, if you have 2m coming with the same velocity and picking up a mass m, that is not going to be the same as just having the m come in. Because now you have twice the mass, you're coming in with twice the momentum. Twice the momentum, picking up the same mass is going to go faster. So now the velocity of the cart's post-collision is going to be more because you have the same velocity but more mass. So you start with more momentum in the system. So you have more momentum, I'm going to say total momentum, when the two carts stick. So that means they're going faster. Faster than this velocity right here. Because instead of this, you would have 2m square root of blah, 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 equals, now it would become 3mx. So it would be 2/3 root, like this. And here, it's the original half, so now it's actually only 2/3 the other one.